Alrighty, everybody. Sorry about that for those folks joining just via YouTube or looking after the fact. I actually started the meeting without turning on the stream, so that's my fault. I'm kind of batting 1,000 here in the last week or so. So I apologize. Next time I'll start right on time. So again, we just started talking about we started talking a little bit about Hampton Plantation, our observing schedule, meeting schedules, which are now posted, and then we started talking about light pollution, the fact that Charleston is looking at a light pollution ordinance, which we're really excited about. Yeah, Tim, according to you, per your comment, yeah, sometimes, especially when you get like a little bit of low clouds or any kind of fog or a lot of humidity in the atmosphere, it's really amazing the amount of light that's being cast upwards, right? And it's just unbelievable. Plus all the LED light fixtures that are like 5,000 temperature, just unbelievable now. So yeah, hopefully we can get that under control. Because it's great to actually have. Sorry, I'm gonna actually close one of the windows because looking at the video stream, it's delayed. So I'm actually seeing myself massively delayed. It's quite distracting. So we're gonna watch that pretty carefully. And fortunately, one of our members, Tom Berta, is involved with that in Charleston, involved with the representatives who are pushing that. So we're gonna have to we'll try to stay on top of that and figure out if they have some success, maybe there's a model that we can then use in some of the communities in the Grand Strand. So because Charleston has, I mean, it's not a rural area, so it's a more metro area like the Grand Strand is. So whatever they come up with likely will be something that can be made workable in an area like this. So assuming that it goes through, but right now there appears to be some support for it. So that would be really nice. Hampton Plantation, as far as being a dark sky site, we continue to work through the process. Per Denise's question, there are two factors, of course, working with the IDA, but also because it is a state historic site, the state of South Carolina. There's a number of things that have to be run through the state, the state level management for the state park. So it's just taking a while to kind of grind through that. That doesn't really affect us for observing. We will still be observing. And like I said, they've been very supportive of us, and we've had some good evenings out there. So we'll be able to move forward, but we are continuing to try to push the dark sky park designation. With all the different measurements and the plans, and we've drafted a lot of the plans are drafted, and a lot of the proposals are there. I know the state's looking at some of them to make sure that they're compatible with all the rules and regulations of the state. There shouldn't be any problems, but you have to get everything approved through the right sources. So we're still continuing to work that, and hopefully we'll get some progress here this fall. There was a big meeting at the end of May between the state management all came down to Hampton to look at it. So hopefully we'll be in pretty good shape. So the good news is that we're not waiting on any kind of lights or anything like that. They've gone to full cutoff fixtures, and they kind of control their lights. All that's already in place for Hampton Plantation. So it's more some other details regarding exactly how they'll be accessed, and some things like that. For the that are part of the IDA criteria. So hopefully we'll have some good news on that in the fall. We also should have some good opportunities coming up this fall for some public observing, because we should start getting some planets back. And I guess I'm sorry.
Hey.
I'm sorry, Tim, it just was.
I said, yay.
Oh, yay. Okay. Yeah, some planets will be coming back up. Of course, we have Mars coming up pretty nicely, I think, and I think that's around December. I know I keep bringing that up, but I do want to keep that in mind. So I think let's see. I don't know how big it's going to be. I'm going to go look. I'm just looking it up real quick. Let's see. Okay, the opposition will fall at on December 8th. So I was trying to find out the Mars opposition size. This time it varies. The size varies quite a bit, as well as the altitude, right? Mars opposition 2022. I'm sorry, trying to look it up. I should have had this looked up beforehand. Yeah, so it looks like it's going to be right around the 1st of December. It's going to be over 17 arc seconds in size. That's right now. If you've looked at it like right now, it's somewhere between 6 and 8. So it's going to be over double the size it is right now. And that's usually a pretty good size. I mean, it's not as big as a couple of recent ones, but still pretty good because it lets you see some detail on Mars, or see some detail even with, like, a relatively modest telescope, right? So again, right now it's somewhere between 6 and 8, and it'll go up to 18. So it's going to get more than twice the size. Let's see, on December 1st, let me just translate from sidereal time here for everybody. Yeah, it looks like it's going to be pretty high in this, relatively high in the sky as well, right? Let's see. Yeah, it's going to be pretty high in the sky. So it looks like it's going to be approaching maybe 25 degrees. In terms of declination. So it's going to be pretty high in the sky. So that's the good news. So between that and the decent size, again, not quite as big as a couple of the previous ones, but still almost 18 arc seconds is going to be pretty good. So I think it's a good opportunity not only to get some good pictures for anybody who wants to do webcam pictures, but it's a great opportunity for trying to arrange some public observings, because usually the winter here, the weather's a little bit better, and the skies are a little bit clearer and steadier. So it's it should be actually, that 25 degrees declination is fairly high in our sky. So it should mean that pretty much wherever we do any kind of event, we should be able to see it. So I think, and the thing is, it's not like it's just one day that it's close, right? It's going to have that size of being over 16 arc seconds will last for quite a bit. So probably like at least like 2 weeks ish. So that's the good news. If anybody has never seen that, never seen Mars when it's close, and you can, like, see surface detail on it, and of course get a nice view of the polar cap, it's well worth doing. So like I said, it doesn't take a huge telescope. A 6 or an 8-inch telescope will show you quite a bit of detail, especially on a night with decent seeing. So definitely not to be missed. I'm not sure if anybody got a chance to see the last, it's about every 28 months you have one of these. I'm not sure if everybody saw it. And what was it, 2020? Yeah, 2020, October 2020, when it was overhead. That was pretty nice. Of course, we weren't doing any any public events then, but because of COVID. But I think it'd be pretty. It was pretty cool, and very very bright and very very bright and very very prominent. Not won't be quite as big as it was last in 2020. If anybody looked at it in 2020, let's see, how big was it in 2020? And let's see. Just trying to see how big. Yeah, it was pretty bright there. So in 2020, it won't quite be good, but it'll still be pretty good. So yeah, let's see. Yeah, it was a little bit bigger. It was about 4 arc seconds bigger in 2020. The best, of course, was in 2018, but still 2022 is not bad. And 2022 is going to be better than, well, pretty much the next till 2033. So for like the next 10 years. So definitely we want to get a chance to get out and do that. So we'll try to organize some events around that, around Mars, right? So that we can see Mars. Maybe we can also organize something. If people are interested, we can organize something maybe in conjunction with the Low Country Stargazers and get a couple people to bring out a couple larger telescopes where we can see a lot of really good surface detail. So we'll see if we can do that. So that's something. The other thing, I didn't have a specific agenda today because I thought we'd probably want to talk a little bit about the web images because everybody kind of talking about that as they came out this week, and it's kind of cool. So I thought, we would just go ahead and talk a little bit about that rather than, unless anybody else has any other topics they'd like to talk about this month. Has everybody seen the web images? Looks like Denise has finally landed. And so yeah, so everybody who's seen the web images, those are very, very cool. They did a great job with those. Kind of interesting, especially the galaxy images. Of course, I'm interested in galaxy images most of all, with the deep field. And it's pretty amazing considering that image really didn't, compared to the Hubble deep fields, which took a very long time to expose, it really really didn't take us that long to expose. The galaxy image is really cool because there's really some neat things you can see in it, right? One of the coolest things is you can see a lot of gravitational lensing. I don't know if anybody's looked at that. We saw all those smeared out galaxies that are actually being lensed. They actually are behind some of these other galaxies and the galaxy clusters in there, and the light's getting bent around. So you're getting these ring images of the same galaxies kind of reflected or in the circle in that elongated format, right? Which is really pretty cool. And there's actually that one that's sort of like maybe at 2 o'clock from the big star. That's you can see that galaxy is very warped as well. So it's getting lensed, and it's kind of cool. You only see it on one side. Maybe you see a reflection on the other side a little bit, but that kind of indicates it's not right behind it, whatever the biggest center of mass is there. But it's kind of really pretty cool. So I really thought that image was great. And they mixed that with a bunch of different filters and mixed a bunch of different colors in, right? So there's some pretty old galaxies in there. So of course everybody notices the diffraction spikes too, right? Which are pretty cool. Again, that's coming from the optics of the telescope, right? So just in case everybody's curious about that, I actually had a pretty good little infographic on that for those that are telescope savvy here. Let's see. So it's pretty cool, right? You can see these same kind of diffraction spikes. We can see these in our telescopes, right? You can even see it in your in a camera lens, right? So you see it, like say if you have a Newtonian that has like a spider holding that secondary, has the 4 lines, then you'll get like the 4 or the the the, the 4 points diffraction lines. In fact, some people like it so much over their telescope, they actually like go put like pieces of wire over their telescope, the front lens of their telescope, just to give those diffraction spikes, right? You can also see it, interestingly enough, you can also see it if anybody's ever done any imaging with like say a DSLR. And if you've ever looked inside one of those camera lenses, you know, have that diaphragm for the aperture that allows you that sort of like, it's almost like a little bellows thing that or diaphragm that squeezes down or opens up. Most of the time people shoot wide open, but if you start bringing it down, because the diaphragm is no longer perfectly circular, it actually is kind of squarish, it'll start putting diffraction spikes in all your stars. So if you're ever taking out your DSLR, sometimes go out there and dial up the f-stop really high and take a picture of a bunch of stars, and you'll see a bunch of diffraction spikes, right? So sort of the same thing here with the Webb. Well, let's see, not very. So because of course the Webb has, you know, struts as well, right? Just like a spider, right? But it has a 3-way instead of a 4-way, right? So what that's going to do is that's going to give you a different kind of diffraction pattern, right? Like the Hubble has a regular traditional spider, so you get these 4 primary things. The Webb is going to have basically 8, if you will, and that comes from 2 places. It comes from the struts, but it also comes from the mirror, the fact that it's not round, and there's actually some gaps. So if you look at the primary mirror, the kind of cool thing about that is like if you have a regular circular mirror like we do, and if you do the image, or you look at a point source image like a star, right? And you're going to have all this diffraction pattern, the circular diffraction pattern. Pretty much everybody sees that, right? You know, like if you try to do any collimation on your telescope, you can defocus you can focus on a bright star with any of your telescopes, and you can defocus it. And if everything is perfectly lined up and the atmosphere is really steady, of course, you'd see these circular patterns, right? Also called an airy disk pattern, right? But it's basically a diffraction pattern, right? The cool thing is that has to do a lot with the shape of the mirror as well, right? If you use a square mirror, there's no reason you couldn't, other than, you know, well, we look kind of funny in the telescope, but you would get a diffraction pattern that would look something like this. And then if you use hexagonal mirrors, which the Webb has, right, a series of hexagonal mirrors, you get this 6-way diffraction pattern, right? So and of course you see these struts, right? So I'm sorry about that. You see the struts, and basically like if you had a single one in there, you get a single one, a single line. If you had, you know, crossing like a traditional spider, you get those. If you have a 3-way, you get this weird 3-way thing. So you get this kind of like squashed three-way thing, right? So when you kind of add all this together, that means, you know, like the strut influence and the primary mirror, that's why you get these like weird 8-point things, right? So that's kind of why all the stars look like that, right? And you know, it's like it's just a fact of the way that the telescope is made, right? So, and of course, you see them pretty much with bright objects, right? Because after all, the Webb's not really designed to look at bright stars. You know, it's like it's designed to look at a lot of faint things and all that. So, but when you start, you know, when you get really bright objects in the field, you're going to get these kind of effects, right? So maybe that's more than everybody wanted to know, but I thought I'd just share that with everybody about why they happen to look like that, you know. And you can kind of see again. So I'm looking at let's see if I can. I probably should have just shared the picture here. if you look at the image, you can see exactly that, right? It's a little tough to see on my monitor. I think my resolution is very good here. But you can see, you've got basically the 8 points. Get the, oops, sorry. Get the one coming across like this, and you got these are combined, and you get that. So you kind of see that, and you can even see it here. Look at this bright galaxy, which is actually pretty cool. This is right above the one that's the kind of lopsided one that I think is pretty cool. But if you come up here and look at that one, oh, sorry, if that one right there, you can see even though that galaxy's got a fairly bright core, and it's actually doing the spiking thing as well, even though you can see the arms. So it's actually pretty cool. So does anybody else have any favorite images from the web that they saw? Or did you all like the deep fields or Stefan's quintet or?
I think the exoplanet data that they got back was really cool.
Yeah, did everybody see that? So what that's about, and let's see. Sorry, I was just kind of Googling on the fly here.
They have like the data chart shows mostly water, but I bet you there's other elements in there too. That was sort of cool, that chart, that graph that's out there floating around on the internet.
Yeah, so this is actually one thing that was when they were doing the web, and again, I'm kind of scrambling to share the image for especially for those folks. This exoplanet, this is WASP 96b. So for those of you that okay, well, let me save that image out as well since it's not expanding for me. And so this is WASP 96b. For those who are not familiar with how they name it, they the way you have the star name for exoplanets, you have the star name. In this case, it'd be WASP 96. And then the star is actually A, and the first planet out is B, second C, second D. So that's where you get the 96b. One of the things that's interesting is this one's actually fairly close. And one of the things the web was actually designed to do, that's kind of exciting, is to start characterizing atmospheres of some of these exoplanets. And the way you do that, of course, is there's really there's a couple different ways. One of which is that when the exoplanet passes in front of the star, right? Of course, the star is going to get a little bit dimmer. That's how we know the exoplanet's there, and you can actually, by doing a little bit of math, you can figure out the radius, and you can also infer the mass of the planet. But which, once you know that, kind of gives you an idea of the density of the planet itself. But one thing with a more sensitive telescope, with more sensitive spectroscope, but like the web is that you have the ability to, some of that starlight, of course, a lot of it's blocked by the planet, but some of it actually passes through the atmosphere of the planet. And so when it does that, the planet's, depending on what's in that atmosphere, it's going to absorb certain indicators, or it's going to absorb certain wavelengths in accordance to what molecules or atoms are in the atmosphere. So that's one of the exciting things, because when you can do that, you can get an idea a little bit about what's going on with the planet itself, right? So obviously the best case would be you would look at a planet that was Earth-like, and then you would find a significantly modified atmosphere. By that I mean, modified atmosphere would have, like, for example, a lot of oxygen in it, maybe some methane, and then ideally what you would find, if it was an industrialized society, you would see that there's a lot of, like, industrial compounds or not very naturally occurring compounds in the atmosphere. If you were to look at Earth, if you were very far away from our solar system, you were to look at Earth like that, you'd see, and you watch the Earth pass in front of the sun, you would see all kinds of exotic and industrial chemicals in our atmosphere, right? Which would indicate there's something going on there. So this is actually the one I have up here. This is actually the one they put with, this is actually a hot gas giant, so it's not Earth-like planet. But you can see there's some really interesting things. They indicate some of the water lines on the spectra. It's interesting when you look at these kind of spectra. They're not, you know, a lot of people think that spectra are like, you know, these really distinct lines, but actually they're the spectra out in nature. There's a lot of phenomena that help kind of broaden out the lines, and interpreting them is like a pretty big art. And it's interesting. It's interesting. The Webb is so good. It is going to be so good at spectroscopy. It has the way it does that, actually, for those that you don't know, is of course the mirror is actually quite big, and you can actually pick up quite a lot of things. So the way they kind of isolate down to one object is they have this array of what they call micro shutters. And I can't remember how many micro shutters there are. I mean, there are thousands. And what they can do is then they can just basically open up one little shutter to kind of isolate one part of the image and get a really good a spectral image. I'll have to look up how many there are in the, oops, sorry about that, in the array. But it's actually pretty cool. And this is, again, this is one of the things that Webb was designed to do. Yeah, it's like the looks like the shutters all measure like 100 by 200 microns, or about the size of just a couple of human hairs, right? So it's actually pretty cool, right? How they can actually isolate one part of the image and get this kind of detail. So sorry, there are 250,000 individual windows. I was off by quite a bit. So yeah, I thought that was pretty cool. Let's see the other one. Let's see the other one. Let's pull up Stefan's quintet. Bum, 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 bum. Sorry, I didn't actually prepare anything for this. So Stefan's quintet, and this is a set of interacting galaxies. Does anybody know where? Just out of curiosity, anybody know why these are famous? Well, they're famous because if you ever watch the movie "It's a Wonderful Life," at the beginning when they had the picture, and you know, there's like the picture, the outer space picture, and they have all the voices talking. It's actually Stefan's quintet. It's just one that was taken, you know, like almost 100 years ago. So it's interesting how I compare that picture with this one. So, and you can see this one, and you can see a lot more interesting things because of the near infrared images. You can actually see like a lot of the gas in these interacting galaxies here. You see these two, and you can see there's a lot of hot gas here. It's actually pretty cool.
Isn't that supposed to be an explosion where I guess the star actually blew up?
I think you're probably thinking of the Eta Carina picture.
Okay, wasn't sure.
I think that's just interacting. I think that's just interacting gas from the galaxies. I think the one you're thinking of, you're thinking of the Eta Carina or the Southern Ring Nebula. Let's see, I'll pull those up as well. Now, Eta Carina is, let's pull up Eta Carina. That's actually very cool as well. Okay, this is the Eta Carina one. And then this is the other one is going to be the Southern Ring. And these are just two different images. One's in the near infrared, but two different infrared images, right? Showing you different parts of it. Which is kind of interesting because you see this star is much less brighter here, right? So it's putting out a lot less energy in the far infrared. I think far infrared is on the right. Yeah, yeah, the mid infrared. Sorry, not far infrared, mid infrared. So yeah, this is the near infrared. So near infrared's, you know, pretty much just off the visible. You know, it's like, you know, for example, we use a lot of near infrared. Like you look at your remote control, most of your remote controls are near infrared. A lot of your digital cameras will pick up near infrared. It's kind of interesting. Like if you have a DSLR again, and you like take your remote control and you point it at the DSLR and push the button and you take a picture, you generally see the light lighting up, right? Because it's can be sensitive to the near infrared. So, but you can see more detail. And then when you go to the mid infrared, you're seeing more heat-ish kind of things, right? And so you see just it accents different things, right?
Yeah, the one on the left is just sitting there, but the one on the right, you can see where the actual explosions are coming off from 10 o'clock, 5 o'clock, 3 o'clock, and 11 o'clock.
Right. You can see the various, yeah, the waves of stuff. Yeah. You know, so that's one of the cool things about looking at things in different wavelengths, right? Is you can see different things, right? It's a great image, very nice image, and some really good detail in the image. Let's zoom in a little bit. Of course, this is all gas, right? And of course, the reason you're seeing it is it's being excited by, or it's been excited, so it's got a lot of energy, right? So, and you can also see different, like it. I think as you were pointing out, Tim, you can see where different, gas could be catching up with gas that was ejected previously and things like that, and interacting. So you see these various waves running through it. As these stars get later on in their lives, if you're not big enough to just completely explode. And this one, I'm not sure. Was this one actually the result of a supernova? Not really sure. No, this one actually wasn't a supernova, according to the web page. It actually basically was just a star bigger than the sun, but it basically just one thing that happens is when stars like our sun get in later life is they start getting variable, and they puff up, and then they shrink back down, they puff up, and in the process they lose a lot of material, and then by the time they get to the end of their lives, it's just a hot core left. All the upper level material has been ejected, and of course that core, a white dwarf, is very, very hot, and all its radiation will actually cause the uh, gas to glow, right? Which is why you kind of see that. And it's kind of interesting. This is not completely circular, right, or spherical, which means it shows you how chaotic it can be when the stars are go through their variable phase where they puff up and shrink down and puff up and shrink down. So it's kind of cool. Does anybody else have any favorite images or anything?
They compared to mountains which are, I guess, millions of light years high. I forget the name that they called it, but you had it up there briefly when you were,
Yeah, that's the Carina one probably, I think. Yeah, and this is, you're seeing a lot of the gas and dust, right? So in the Carina Nebula, this is where you have a lot of stars. There's a lot of hot, young, bright stars that were born in this area, and their radiation is sort of blowing out the gas, pushing all the gas out, right? It's a big gas cloud that collapsed, formed a bunch of big stars, and now it's being blown out, right? So that's kind of what you're seeing here. Because there's a bunch of bright stars that are kind of pushing all that stuff away. But yeah, it's actually very, very cool, right? So those are very young, hot, bright stars. It's actually quite a nice object if you're in the southern hemisphere, right? At a Carina Nebula. But we can't see it from where we are, so.
field trip.
Yeah, that would be great. Yeah, it'd be great to go to the southern hemisphere, but kind of hard to bring all your equipment along, you know? But we get to see things they don't, so. Yeah, it's actually great that the web actually has turned in such great images, right? And works very, very well. So the great news, that's great news because, you know, you can't really go off and fix it because it's quite a long ways from Earth. So it's good that it works. It's not something that's realistically serviceable. So the fact that it works right the first time is great. It'll be really interesting. They'll be researching some of the oldest galaxies, and as well as trying to find evidence or of some of the very first stars in the universe. Although I don't think they'll actually be able to see far enough with enough sensitivity to see the first stars, which we theorize were very, very massive. But they think they'll be able to see basically the signs or the after effects of those stars. And of course, the exoplanet stuff is very exciting. You know, characterizing some of the atmospheres on the exoplanet. And I guess I didn't really talk about this, but another thing that they're going to try, another way that they look at these exoplanets is not necessarily just seeing all the light come through the atmosphere, but there's and I read some very interesting papers on this, you know, maybe 2 years ago, that one interesting thing is like using indirect light. Well, what I mean by that is if you've got, like, say you've got a star right here and then you've got a planet over here, well, the planet's going to be reflecting light, right? Some of that starlight, but it's not like a perfect mirror, right? Like if you were to look again, if you were far away and you were looking at Earth going around the sun, you were looking at Earth, it would be blue and green, right? Blue is pretty common for planets, you know, or you get a lot of things like, you know, like Uranus and Neptune are blue. But what would be really interesting is if you were to look at that on an exoplanet, you were to see green. It turns out green is not very common, you know, in terms of, you know, things you see out in space. So if you were to see something had a distinct green hue, then that would be really interesting because that may indicate that you've got some kind of biological life going on. So you can actually, the reflectivity also tells you stuff about planets as well. So hopefully they'll pick some really good ones to try to characterize here. And hopefully we'll see some really cool science coming out of that. I don't know, Denise or Ronnie, do you have a favorite image or?
No, I don't have any favorite ones. I just enjoy them all.
Yeah, well, that's fair. That's very fair. So
I think I like the quartet, like the Stevens quartet. I think that's my favorite one, I think.
yeah, that that is a pretty good image. There's as much as I like the deep field, because it's kind of what I do. But yeah, I think this is actually just really fascinating. Looking at these the different galaxies, right? And
Right. They're the different types, right? You've got like the spiral, and then all the different types, right? What are the other types? The bar
yeah,
spiral,
so
the irregular.
these are heavily disrupted. Like you can see this was probably a grand design spiral, and all that means when you say grand design spiral is you can see the core right here where my I don't know if I don't know if you can see my cursor, the hand shaped thing. Um, but it's got an arm coming off this way and an arm coming off this way, right? So that was probably a grand design, what they call grand design spiral at one time. But you can see it's pretty disruptive with this one. This one might have been a spiral. This one certainly was too. But you see all these long tidal tails, right? When these galaxies like interact and merge, like two galaxies, galaxies are mostly empty space, like more than 99%. So when they collide, they really just sort of pass through each other, but they do a lot of disruption in the patterns, right? And then a lot of times they can get in these patterns where they just keep coming back and recolliding and redisrupting until they finally form something, a new resultant galaxy. See this one over here on this side, the left-hand side looks very disrupted, right? So it's pretty cool though. And again, that's probably why you have all this hot gas, right? It's probably, it looks like there was an interaction somehow because there's this long tidal tail of stars stretching out, right? And then you can see a lot of hot gas here, which is probably a result of some of that interaction, or maybe been stripped out of one of those galaxies. And you see, probably got some good star formation going on there.
When I was in the astronomy club back in Pittsburgh, we had a lot of scientists come and talk, and one gentleman did galaxies, and he said when they collide, you're right, they kind of miss each other and they come back and forth, miss the handshake and all that. He says, but whatever is solid in there, it never gets destroyed. Like if there's planets in there, they won't get destroyed. If there's stars in there, they will not get destroyed.
Right. Yeah. And they'll end up in somewhere in the new galaxy over time. So that's why you get these really cool patterns. Like see this long tidal tail here. This is pretty typical of some kind of interaction that has stripped a bunch of material out there and either stripped some star systems out, probably some star systems and some gas, and formed new stars. So, but again, there's still gravity associated with this, so they'll eventually collapse back in.
And I have a question. When I teach kids about galaxies, we do real basic. We classify them as spiral, elliptical, and irregular. That's like our 3 classifications when I'm teaching kids about galaxies. So, I mean, obviously, I like this picture because it's going to be something I could probably use in the classroom. Now, that one towards the bottom, that almost looks like egg shaped, that would be irregular. Is that correct? Like, I want to make sure that if I'm using this picture in the classroom, that I'm classifying these all correctly. The ones with the arms are pretty easily to see, the spiral arms,
Right.
So I just double
Yeah.
checking on all that.
Well, this would probably be an elliptical, the one on the bottom.
Okay, that would be elliptical. Okay.
Yeah, a regular would probably be more the one on the top.
Okay.
Because it's been disrupted. One of the things about the galaxy classifications is they're sort of general. It does take some expertise to do it, but even sometimes experts don't agree. I had a graduate class on that once, and yeah, they had us classifying a bunch of galaxies and then go looking up other classifications that people had made. It's really very interesting.
Yeah, for kids, I try to make it really basic and simple, obviously. And I'm looking at this data too. Like we could load up Galaxy Zoo now with a whole bunch of new data, I guess, on the Zooniverse project. A lot of these projects can be probably expanded from all this web data too. So I wonder how much citizen science we're going to be involving with the web. That'll be interesting as well to see, if we'll have people doing those kinds of projects.
Yeah, looking at some of the data and things like that. Yeah, because there'll be a lot of data. I mean, I think the web is generating, I can't remember, what, 214 gigabits of data a day or something. So there's going to be quite a bit of data. So that's one of the big challenges, of course, is you know, is processing all this data, right? So it used to be a case of where the data was manageable by like the various teams, but now there's so much data that citizen science is one way to solve that problem, is to have people like if you're looking for patterns and stuff, have people which are really good at seeing patterns doing that, and then that kind of gives you some ways to like kind of narrow in on what you're looking for. So I don't
But
know of
what
any
do you
particular projects with web, but we'll see.
Yeah, hopefully there will be. But I wonder about citizen science and AI. Like, is AI going to take over all these citizen science projects? But I love the idea of people contributing, though. So that's a big question I think about a lot. Like, I don't want the AI to take over.
Well, I've actually got a talk all about that. So I'm trying. I guess I didn't do that for the Grand Strand Astronomers. I did it for the Low Country Stargazers and I did it for the Greenville Club. So I guess I should schedule a talk for that.
Oh, is it on? You mean a talk on an AI? You mean
Well,
or?
it's machine learning and citizen science and astronomy.
Okay, yeah, because you don't want it. That's what I'm concerned. We did spirograph for you with you. I remember we did that
Right.
a long time ago.
This is a little bit different. This mainly is more general for like where machine learning, which is what, AI, and where it's being used, and some of the challenges and comparison with like citizen science. So I'll if people are interested, I'll give that talk. And you
Yeah,
know,
that's another good one. And again, the sky site one, I would just love to know the process and the ins and outs. That's another talk I would love to hear about, or where it's at, where it's going in Hampton Plantation, and what the beginning point is, and how to get to that end point. It would be interesting as well.
yeah, maybe I'll try to see if the person can also talk a little bit about what's involved in a dark sky. So anybody that's talking with their neighborhood or their community can, kind of talk about some of the common sense things that can be done.
I mean, when you guys are out there, are you out there with a light meter measuring with all of you when you're out there doing it?
So we actually are. That's one of the requirements, is that you regularly take sky quality. It's called sky quality measurements. There's actually some devices that do that. So some of the folks in Low Country Stargazers do own those devices, and so they have been out there. I think they were out there in April, and I think they took some measurements in June as well. And the idea is that's how you tell how dark the skies are. So it's one of the things you can do. So some pretty cool stuff, cool technology. And so hopefully that will keep rolling along. The dark sky stuff. So go ahead and unshare that. All right, so it's kind of a quiet group tonight. So again, I apologize for all the confusion on the meeting dates. Does anybody have anything else they want to talk about?
We are good.
I think we are good. Okay, well then, first of all, I'm going to go ahead and thank everybody who's watching on the YouTube stream. So let me stop.